Good morning. This is Professor Alan Haungs, SUNY at Fredonia. Um, Physics 124, Oscilloscope Lab. This is basic concept number 3.5. I realized I had to add this in after I looked at the my videos to make a smooth transition of the idea. Um, we were talking about signals a lot, and signals can be pretty complicated. Signals can contain both AC and DC simultaneously, and that's done purposely by engineers for reasons, for good reasons. I'm not going to get into the reasons, but here's an example of a AC, a symmetrical AC, that is superimposed upon a plus 1 volt DC. So it goes all the way up to 3 volts plus and down to -1 minus. So it spends most of its time as a positive voltage. It's on this side of the zero line. It spends a smaller part of its time on the negative part of the graph. There are circuits that purposely combine AC and DC voltages when you're talking about signals. This would never happen with power. It should never happen with power. Okay? We also have circuits that not only combine it, we have circuits called bypass circuits and decoupling circuits that can look at a signal like this, superimposed on a DC. That DC could have been down here or up here, could have been 1,000,000 volts DC, that you have a small little ripple AC riding on top of 1,000,000 volts DC, or it could be 1,000,000 volts AC and riding on a 1 volt DC or something. So you can have all kinds of combinations. But we have circuits that not only combine it, but also decouple it or bypass things. So if I was only interested in the AC component on my oscilloscope, I push a button and it only can see the AC. The DC component is completely gone. Or on my scope, I can see the AC and the DC. My scope will not allow me to see only the DC. That I have to figure out myself. But there are circuits that do that. They can pull out only the DC, and circuits that can pull out all the AC. Now, because of this complication of a circuit, this voltage here has 3 voltages. It has a DC offset, of 1 volt. Okay. It has an AC peak. So see this AC is running symmetrically on either side of this DC value. It's swinging 2 volts this way and 2 volts that way. Okay, so it has an AC peak value. So it doesn't matter how high or low on this graph that DC offset takes it, it still has the same voltage peak. And because it's and a lot of times, because of this DC offset, we're also interested in the peak-to-peak voltage of the AC component, with the DC component superimposed, but that doesn't affect this number. So that swing peak-to-peak is referring to the AC component. Now, if it was in a power situation, we wouldn't care about the peak-to-peak voltage because it's symmetrical. It's a symmetrical sine wave, and the V peak is the same as the V peak to peak. But in a signal situation, this peak to peak might be actually the more important and more interesting value because it may not be symmetrical around the 0 point, whether that 0 point is truly 0 or if it's a DC offset. So there's a little more complication here with signals. Having said that, okay, so you see how the peak to peak is measured, how the peak is measured, and how an offset, a DC offset would be. An offset can also be called a bias. Okay, now let's talk about power. Okay, in power, we would never mix AC and DC in a circuit. Okay, now the oscilloscope was mainly dealing with signals, but we're gonna use it for a power application. You'll do that. You'll see that in the demonstration. So in AC, we wanted to simplify things. So we started with a simple model. We say, in a DC situation, if I have a certain voltage across this battery, that resistor will heat up a certain amount. At a certain DC voltage, that'll heat up a certain amount. I want to know what voltage I have to put across that same resistor if I had an AC voltage to make that resistor heat the same amount. And so they come up with this idea called RMS, which means root mean square, which means to you, not much, but what it means to you, what it should mean to you is it means effective voltage. I want to have the same effective situation with my voltage in AC as I did in my DC. So if I have to get rid of my DC source, I have to use an AC source, I want to heat this resistor, the same resistor, the same amount, what RMS voltage would I use? Well, if it was 100 volts DC here, I would have 100 volts RMS over there. If that was 100 volts RMS here, or if this was 50 volts RMS here, I would have 50 volts DC. So RMS, from a power application, the RMS voltage from a power application is its equivalent to had it been DC. Okay? So how does RMS voltage relate to voltage peak? It's a very simple arrangement. It so happens that if your AC voltage goes up to the peak voltage here, we won't worry about peak to peak. I know in the laboratory it talks about peak to peak, gives you a different formula, but with AC power we're talking symmetry and that, so I'm just keeping it simple. Okay? This is your peak voltage. If you want to know what RMS value, by the way, all the power that's delivered to your house is rated in a voltage called RMS, all of it. When you use AC power, not signal, AC power is always volts in RMS, okay? They never tell you what the peak voltage from here to here is. They never tell you. You don't say, the power the power line in front of your house is, 18,000 volts peak or something. They don't do that. So they tell you the RMS value. The RMS value is just simply the peak value divided by the square root of 2. It's that simple. Okay? And if you were given the RMS value, you could calculate the peak value just by multiplying it by the square root of 2. So if I said to somebody, gee, I have this 12 volt battery that I'm heating a resistor with, 12 volt battery, and I have to know 12 volt battery DC that we're pretending. So this is the power equivalent. This is an AC voltage. RMS is AC, but so if I have a 12 volt battery DC and what kind of peak voltage would I need on my AC to be able to get to there, right? What kind of peak voltage would I need on my AC to get to that DC equivalent? You see how that works? So this is a convenient way for power, because in power we're not talking about the shape. The shape is always the same when you're talking AC. We're not superimposing a DC voltage on top of it. It's either AC or DC. That's how power works. That's conventionally. Maybe some smart engineer one day will figure out to combine them both for some reason. Maybe. But that's not happened yet. That's not the convention. So you'll see in the next video an application. We'll use the oscilloscope. So I had to add this little lecture to make that one more clear. You guys have a great day.